Sobolewski from Krakow, who speaks on monochromatic arithmetic progressions. Please.
Thank you very much for the opportunity to give a talk at this conference. And I will be speaking about monochromatic arithmetic progressions in binary words associated with pattern sequences. So let me start with some motivation, namely the Thue-Morse sequence, a very, very famous, well-known sequence. I will denote the whole sequence as both T and its terms by Tn. And here Tn is the sum of binary digits of n modulo 2, which can also be viewed as the number of ones in the binary expansion of n, and this interpretation will be important later. And equivalently, one can define the sequence by setting T0 equal to 0 and these recurrence relations. And here are some initial terms of the sequence. And one can observe that if we take a block of length 2 to the power k from the beginning, then the next block of the same length is the negative of the initial block. So this is a way to generate the initial terms of this sequence quickly. And well, this is a sequence of zeros and ones, and throughout the talk, I will identify the sequence with an infinite binary word, so the terms of this sequence concatenated, and a coloring of the set of non-negative integers. So a partition into the set where Tn is equal to 0 and the set where Tn is equal to 1. And since we have a coloring, we can talk about monochromatic arithmetic progressions. And I will say that n and plus d and plus 2d and so on is a monochromatic arithmetic progression in T if the values at these indices are all equal. And here this progression can be either finite or infinite. As we will see, there are no infinite arithmetic progressions in T. And the result of van der Waals implies that there are arbitrarily long finite monochromatic arithmetic progressions in this coloring or in this word. And some natural questions are, well, whether there exist infinite monochromatic progressions, and where can these arbitrarily long finite progressions be found? And for a given difference of such an arithmetic progression, can we bound the maximal length of a monochromatic progression? And the answer to the first question is no, which follows from a result of Gelfond, which is more general than the version I am showing. However, this is adapted to our case. Namely, if we pick a binary digit, 0 or 1, then this digit appears with frequency 1/2 in the Thue-Morse sequence taken along the arithmetic progression dn plus a. And here we have an error term x to the power lambda, where lambda is some number less than 1. So in particular, we see that in every arithmetic progression, there exist infinitely many ones. I mean, the Thue-Morse sequence attains the value 0 and 1 infinitely many times. So there cannot exist infinite monochromatic arithmetic progression. And in order to give answers to the other posed questions, I will need some more notation. So for non-negative integers n and d, where d is greater than or equal to 1, we define the terms AT of ND and AT of D. So basically, AT of ND is the longest monochromatic arithmetic progression starting at N of difference D. And AT of D is the supremum of these values. So this is the longest arithmetic progression, monochromatic arithmetic progression of difference D starting anywhere in the coloring or in the Thue-Morse word. So for example, if you want to compute AT of 0 and 3, then we look at each third term of the Thue-Morse sequence starting from 0. So we have 7 zeros in a row, and then we encounter a 1. So this AT of 0, 3 is equal to 7. And computing general lengths of these progressions, so AT of D is a bit more complicated. So let's take the same example with the difference 3. And I will show, without showing all the details, that AT of 3 is equal to 8. So, for example, we can observe that starting at 35, we indeed obtain a monochromatic progression of length 8. So AT of 3 is at least equal to 8, and we would like to prove the opposite inequality. And to do this, well, we can assume for the sake of contradiction then that there exists a longer progression. So somewhere in the Thue-Morse word, there appears a word of this form, where we have 0, then asterisk signifies any binary digit. So there are two binary digits, and again 0, then 2 binary digits, and so on. And this 0 appears 9 times. So we get some word of length 25 of this form. And similarly, if this progression is of color 1, then we get a similar word, but with 1s. So the problem reduces to finding all subwords of this infinite word T of length 25 and checking whether there exist subwords of this form. And here I omit the details. However, one can show that any subword of length 25 already appears in this prefix of the Thue-Morse word. So within the first to the power 8 terms, we can find each such word. And one can check by using a computer that none of these words are of the above form. So we indeed get the equality. And regarding the next questions, we have a theorem of Morgenbesser, Schalit, and Stoll, who investigated progressions starting at 0. And well, here this number AT of 0D can be defined in a simpler form, because this is the least multiply of D, such that the term KD is equal to 1. And managed to give a linear bound on the maximal length of such a progression equal to D plus 4. And this is a sharp bound because we have an infinite family of D such that this becomes an equality. And also the fourth case is interesting because we get another infinite family of differences D such that we have those arbitrarily long progressions. And well, additionally, they proved that we can find an integer n such that the n is equal to 1 of quite simple form, namely its sum of digits is equal to 3. So there are only 3 ones in its binary expansion. Okay, so we know something about the specific positions at which those arbitrarily long progressions occur. So moving on to general progressions. So now we do not restrict our attention to progressions starting at 0. You have a theorem of Parshina, which again is a bit more general than the one I am showing. This is the case of the Thue-Morse sequence. Namely, if we consider monochromatic arithmetic progressions of difference at most 2 to the power k minus 1, then the longest of these progressions, the maximum value is attained for d equal to 2 to the power k minus 1 and given by this formula. And there is a similar result by Aedo, Nagai, Grimm, Steinova, quite recent, where they determined the maximal length of a progression of difference 2 to the power k plus 1, and also proved the expression for the length of a progression of difference 2 to the power k minus 1 in another way than Parshina did. And one can compare these expressions with the values in the previous theorem. And actually, it turns out that in this result, the lengths d plus 4 and d, in cases 1 and 4, are exactly 1 less than the values here. So, in other words, the lengths of progressions starting at 0 approximate the lengths of progressions starting anywhere quite well. And I considered another direction of generalization because recall that Tn, the nth term of the Thue-Morse sequence, is just the number of ones in the binary expansion of n, which is then reduced modulo 2. So we can replace this 1 by any other string of binary digits and ask similar questions. And in order to state this more precisely, I will need some more notation. So here I assume that n is a non-negative integer, and w and v are finite words or strings or blocks consisting of the letters 0 and 1. And by n in parentheses with subscript 2, I denote the canonical binary expansion of n. And by canonical, I mean that there are no leading zeros in this expansion. So if I take n written in decimal, then the expansion is 1010 in binary. And conversely, if we have some binary word, w, then by this word in brackets and with subscript 2, we mean the integer represented by this word in binary. And here, the difference is that we allow leading zero. So, for example, 0, 1, 0, 1, 1 in binary represents 11 in decimal. Also, we define the length of a word. So this is just the number of letters in this word or digits in our case. If we add the subscript v, then we mean the number of occurrences of this word v in the word w. So, for example, the number of occurrences of the pattern 1, 1 in 0, 1, 1, 1, 0, 1, 1 is 3. And here, again, it is important that we count overlapping occurrences. So if you take a look at the block 1, 1, 1, then we have 2 occurrences of the pattern 1, 1, and they overlap on this middle one. So this is important. Also, we write w to the power m to denote m-fold concatenation of the word w. That is the word w written m times. So, for example, 1 0 to the power 3 is 1 0 1 0 1 0. And I will only write this in regard to the binary digits, so either 0 or 1. So there will be no confusion between this concatenation and exponentiation of integers. And finally, we define the binary negation by writing a bar over w. And this is just replacing zeros with ones and ones with zeros. And now the pattern sequences, which appeared in the title. So let V be a finite word consisting of the digit 0, 1. And in this context, I will call V a pattern. And we define EV of n as the number of occurrences of V in the binary expansion of n. This is in the case if the pattern V begins with a 1 or is a pattern of zeros. And there is a convention: if the pattern V begins with some number of zeros but contains a 1, then we present the binary expansion of n with the same number of zeros. And this makes this sequence behave a little bit better. And we call the sequence EV of n a pattern sequence. So, for example, if we have the pattern 1 0, then E10 of 9 is 1 because there is exactly one occurrence of the pattern 1 0 in the binary expansion of 9. However, if we consider the pattern 0 1, then according to the definition above, we have to prevent the binary expansion of 9 by a 0. So in this case, there are 2 occurrences. And moving on, as in the beginning, we can identify this pattern sequence, reduced mod 2, with an infinite binary word, and again with a 2 coloring of the non-negative integers. So in particular, if we take the pattern V equal to 1, then we obtain exactly the Thue-Morse sequence. So this is precisely the situation I talked about in the beginning. And again, we ask the same questions. So do there exist infinite monochromatic arithmetic progressions in this coloring? Where to look for long progressions, and how long can a progression of a fixed difference d be? And can I define similar notation? So this time we have the subscript v instead of t, as was the case for the Thue-Morse sequence. So this is just the longest monochromatic arithmetic progressions in this pattern sequence, starting at n and of difference d. And similarly, we take the supremum of these values over n. So AV of d is the longest monochromatic progression of difference d starting anywhere. And another very famous example of such a sequence is the Rudin-Shapiro sequence, which can be defined slightly unusual definition by E11 of n mod 2. So this counts the occurrences of the pattern 1 1 in the binary expansion of n. And equivalently, we can define R0 equal to 0, and for the following n by these recurrence relations. So usually this sequence is defined over plus and minus 1. But in our case, this makes no difference. And here are some initial terms of the sequence. And in order to distinguish the sequence among others, I will write AR instead of A11. And this is the first result that I managed to obtain for the Rudin-Shapiro sequence. So this is an analog of the result for the Thue-Morse sequence by Morgenbesser, Khalid, and Stoll. So here I focus again on progressions starting at 0. And it turns out that the maximal length of such a progression of difference d can be bounded from above by 1/2 of d plus 3. And in particular, there exists an infinite family of d such that this becomes an equality. And we can also distinguish another family of d such that such a progression is given by a nice formula, d plus 1. I mean, the length of such a progression is given by a nice formula, d plus 1 divided by 2. So again, we get some arbitrarily long arithmetic progressions, which can be exhibited specifically. And otherwise, it turns out that the maximal length of such a progression is less than d divided by 2. So maybe I will skip the proof, because I'm afraid there will not be enough time. And moving on, we have another result for general progressions of difference 2 to the power k plus 1. So why this particular difference? Because this was one of the special cases in the previous theorem, and I wanted to find out whether we have a nice formula for the maximal length of such a progression. And another result concerning the maximal length of a progression of difference 2 to the power k minus 1. Again, this was a special case in the theorem that I gave earlier. And again, we get a nice expression for the length of such a progression. And these results still do not settle whether there exist infinite monochromatic arithmetic progressions in this Rudin-Shapiro world. And the answer again is no. And this is implied by this theorem. So here in the statement, I use the notation mu 2 of d, which is the two-adic valuation of d. That is the largest power of 2 that divides d. So we can bound from above the maximal length of a progression of difference at most 2 to the power k by such a quantity. So in particular, we have a corollary that there is a linear bound. AR of d is at most for d. In fact, I believe that this bound is rather weak. If we ignore initial values of d, namely based on numerical calculations, I believe that for d greater than or equal 23, we have a much better bound with the coefficient equal to 1/2, and equality occurs infinitely often for d of this form. But I think that proving this is rather difficult. And moving on to a general pattern V, first, what happens if the pattern consists of only zeros? And then it turns out that the maximal length of a progression starting at 0 is bounded from above by 2 to the power I. So this is not too interesting. So we can restrict our attention to other patterns. And also I exclude v equal to 1 from the considerations because we already have a result which I gave in the beginning. So let V be a pattern which contains a 1 and ends with j zeros. And we can fix some differences D such that this value AV of 0 dk behaves almost in a linear fashion with respect to dk. And here we have some constant CV, which can be effectively calculated. And in particular, we can exhibit progressions for which we can provide an exact formula for their length, which is given in the formula below. And again, here we have a constant B, V, which again can be calculated effectively. So a corollary of this result is that we get infinitely many limit points of the sequence AV of 0D divided by D, which are of this form. And in fact, I believe that this is the whole set, again, based on some numerical calculations. And also, I believe that one can find a sharp bound on the numbers AV of 0D, where we have the same constant, CV and BV, and the bound is linear. And again, this relies on the calculations. And in general, we have a similar result. So for a general pattern V, again, we can show that the maximal length of a progression of difference D is finite. So there, in particular, there exists no infinite monochromatic progressions in the corresponding sequence. And this carries over to the progressions starting at 0. And also as a supplement, because this term works for V greater than or equal to, of length greater than or equal to 2, we can also prove that the lengths of progressions for the pattern 0 are exactly the same as the lengths of progressions for the pattern 1, which corresponds to the Thue-Morse sequence. So we get this formula, which was proved by Shina for the Thue-Morse sequence. We get this for free. And some problems and questions that came to mind when I was looking at the experimental results. So maybe I will not describe them in detail. However, I think that it's interesting to calculate the upper limits of the sequence AV of D over D, and also describe the values of these sequences and look at the distribution of their values. And also another question to consider is whether these sequences are irregular in the sense of Alush and Khalid. And this is all I wanted to say. So thank you for your attention.
All right, thank you very much. There may be time for one question. If not, then I thank our speaker again. And the next talk will start in 2 or 3 minutes.